Welcome to the Foundry Sand Operation and Maintenance Training video. In this training video, we will cover safety, the Foundry process and processing units, major components and operating principles, preventative maintenance, major maintenance, and troubleshooting. Safety. For your own safety, PPE or personal protective equipment is compulsory. You will at all times be required to wear your hard hat, safety boots, hearing protection, gloves, eye protection, and reflective clothing. Foundry process and processing units. We start at the screen where the specifications process takes place. The design intent is to separate material at 0.8 millimeters. Material from belt CV270 is fed into a sizing screen consisting of 0.8 millimeter panels. The oversized material that is bigger than 0.8 millimeters is fed into the mill. The undersized material that is less than 0.8 millimeters is collected into the foundry feed tank and pumped to the desliming cyclones. The design intent of the desliming cyclones is to remove slimes prior to processing on the spirals. The pulp from the foundry feed tank is fed into a cluster of 3 desliming cyclones, which cuts at 45 microns. The overflow is transferred to the dewatering cyclones, and the underflow gravitates to the collector box, which feeds the spirals. The spiral's design intent is to upgrade the material and produce a product with at least 44% chromite and silica of less than 4%. The rougher stage consists of a bank of 8 triple start spirals, which is fed from a 24-way distributor. The tailings report to the melt recovery tank, and the concentrate and middling report to the cleaner stage. The cleaner stage consists of a bank of 6 triple start spirals, which is fed from an 18-way distributor. The concentrate is regarded as the final product, 44% chromite, and gravitates to the product tank. The tailings report to the melt recovery tank, and the middlings gravitate to the recleaner stage. The recleaner stage consists of a bank of 6 triple start spirals, which is fed from an 18-way distributor. The tailings report to the melt recovery tank, and the concentrate and middlings report to the reflux classifier feed tank. The design intent of the reflux classifier feed tank is to supply the reflux classifier with the feed. The spiral's recleaner concentrate and middling material is collected into the reflux classifier feed tank, which in turn feeds the reflux classifier. Fluidization and makeup water to the reflux classifier product tank is supplied by the reflux makeup water. The reflux classifier's design intent is to produce a foundry product with at least 46% chromite, silica of less than 1%, and AFS of 40 to 50. The design intent of the reflux classifier overflow and underflow tanks is to collect the reflux classifier overflow and underflow products. The reflux classifier underflow material is collected in the underflow tank and is pumped to the product stacker cyclone. The material from the reflux classifier overflow is collected in the overflow tank and is pumped to the dewatering cyclone. The design intent of the dewatering cyclones is to dewater the reflux classifier overflow and produce a metallurgical product. The stacker cyclone dewaters and stacks the reflux classifier underflow and produces a foundry product. Major components of the reflux classifier and operating principles. The complete machine consists of a lamellar chamber, a mixing chamber, and fluidization chamber. The feed distributor delivers the slurry into the reflux classifier mixing chamber via 2 square chutes extending through the lamellar section. The reflux classifier's lamellar chamber consists of a series of inclined parallel plates. The plates are manufactured from PVC and are contained in a series of modular boxes. There are 16 standard size boxes containing 79 plates each, and 2 smaller boxes designed to fit next to the feed chutes, each containing 32 plates. These lamellar plates enhance the settling rate of the particles in the slurry and provide the refluxing action, which has particles slowly sliding back into the fluidized feed zone of the main vessel. Each lamellar plate is of uniform angle and spacing dimension. The overflow from the reflux classifier contains most of the processed water, the low-density solids, and any misplaced slimes in the feed. The internal launders at the top of the reflux classifier direct the overflow slurry into a single discharge overflow launder. This material exits the reflux classifier via the overflow flange. The pressure probes are located at the mixing chamber of the reflux classifier. They are used to measure the density of the bed inside the chamber. At the base of the mixing chamber, high-pressure fluidization water is introduced via approximately 390 alumina-ceramic nozzles and flows upwards, interacting with the slurry. The fluidization water chamber has a pressure relief valve installed to protect the unit against overpressurizing. However, it is essential not to allow the fluidization water pressure to exceed 200 kPa. Exceeding this may damage or rupture the reflux classifier's fluidization water chamber and could cause personal injury. The underflow valve is automated via the underflow control arm, which is activated via an electropneumatic positioner on the side of the mixing chamber. The electropneumatic positioner has a proportional positioner. The material discharged from the reflux classifier's underflow valve typically has a high pulp density and is highly abrasive. Therefore, the underflow outlet is lined with a combination of alumina tile and Ludowici wear-resistant ceramic. The feed distributor delivers the slurry into the reflux classifier mixing chamber. The slurry inside the reflux classifier then undergoes a sorting process due to the force of gravity and the upflow of fluidization water. It is in this sorting process that the separation of high and low density particles takes place. There are several zones of high density slurry within the mixing chamber. At the bottom of the chamber, a higher density bed of settling solids is formed. The high density bed is kept in suspension by jets of incoming fluidization water at the base of the chamber. The coarse and fine low-density particles that may be trapped in the dense fluidized bed tend to be sorted upward due to the turbulent motion created by the fluidization water injected from below. The high-density particles sink to the bottom of the fluidized bed due to gravity and migrate towards the central underflow valve. The low-density particles are held in the slurry suspension, which migrates to the lamellar section of the reflux classifier. The lamellar channels enhance the settling rate of any misplaced high-density solids, which slide down the plates and slowly recirculate back into the feed zone of the mixing chamber. This forms a slightly higher density zone under the lamellar plates. The low density and small particles tend to overflow from the reflux classifier's lamellas in their first pass, whereas the slightly denser and larger particles will require the autogeneous process density within the vessel to rise and enable them to be displaced to overflow. The density of the middle section of the mixing chamber is measured and used to determine when to allow some high-density solids to be discharged from the bottom of the reflux fluidization chamber. The high and low density particles in the autogeneous zone are separated by gravity and the upflowing fluidization water. Below this zone, the high-density solids settle to the bottom of the reflux classifier, forming a dense fluidized bed. The bed of solids will be apparent in the bottom side glass during normal operation and is necessary for efficient operation of the reflux classifier. The underflow is discharged into a collection tin dish or launder. Operating principles. Control. The reflux classifier is controlled by the difference in readings between two pressure probes located in the mixing chamber. This is converted to a relative density of the measured section, which is controlled against the set point. This information is used to regulate the height of the fluidized bed by the use of the underflow valve. Startup. Turn on the instrument air and power sources to the reflux classifier. Ensure that all valves are set to automatic operation. Open the reflux classifier water control valve while observing the flow meter's flow rate. The flow rate should be adjusted to the required rate. Introduce feed to the reflux classifier. Observe the overflow of the reflux classifier to ensure that the feed has been entered into the reflux classifier and no blockage occurs in the feed pipe. The reflux classifier overflow height should increase as the feed is introduced, and shortly after that, solids should be observed in the sight glass. Shutdown procedure. Turn off the feed to the reflux classifier. Bump all slurry from the reflux classifier via the underflow valve while keeping the fluidization water on. Turn off fluidization water only after all the slurry has been drained from the reflux classifier. Visual inspection can be done via the sight glass and torch. Turn off the instrument air and power sources to the reflux classifier. Preventative maintenance. Replacement of the probe sensor. Ensure the reflux classifier is drained and ready for maintenance. Disconnect or isolate the probe to be replaced. Unsecure the PVC casing. The pressure sensor is glued to the PVC case and will come off at the same time. Pull the cable through. Take the new pressure sensor and put the cable through the new PVC. The cable then has to be pulled through the probe housing. Teflon tape the thread of the PVC case and screw the PVC case into the probe housing. Use Sikaflex to glue the pressure sensor into the PVC case. Things to remember about the reflux classifier. The fluidized bed height should not be above the top window. Minor feed bypass to overflow will not affect overall operation efficiency. Channel blockages up to 10% will not affect overall efficiency. Random nozzle blockages up to 15% will not affect overall separation efficiency. The underflow valve is not a perfect seal. It will drip. Keep fluidized water constant unless otherwise instructed. There is only one process variable for the operator to control, and that is density set point. If you increase the set point, you will increase the quality of your underflow content. Major maintenance. Units that require major maintenance include the nozzles, the lamellar plates, and the underflow valves. Every maintenance day, check nozzles for breakage. If the reading on the pressure gauge is high, the nozzles are blocked. If the reading is low, the nozzles are worn. During operation, check for blockages and clean. Block channels can be observed during operation. Check underflow valves annually. Troubleshooting. Leakage of slurry from the underflow valves could be caused by chipped ceramic valve seat or oversized material stuck in the underflow valve or incorrect tailing valve calibration. If the valve seat is chipped, replacement is required. If oversized material is present, then manually open the valve to allow it to clear. If no oversized material is found, check calibration by setting manual valve position to 0. If leaking, then a valve recalibration may be required. Product grade not within specifications, poor fines classification, or incorrect feed particle size or incorrect set point. To fix this, check set point and readjust. Oversized particles in the underflow stream could be caused by faulty screen panels upstream. If the feed is too coarse, check for worn or damaged screen panels upstream. Non-responsive automatic valves could be caused by a loss of power or air pressure. To fix this, check the air filters have good air supply to them with no leaks. If air is supplied, they will have a reading on the pressure gauge attached to them. Check the air lines for blockages. Place underflow valve in manual to see if it moves. This presentation is brought to you by Coleman, Coal and Mineral Processing Solutions.